Okay, for the next part of this, we're going to do problems 11, 12, 17, and 22. The directions for which are: tell the maximum number of real zeros that each polynomial function may have, then use Descartes' rule of signs to determine how many positive and how many negative zeros each polynomial function may have. Do not attempt to find the zeros. Well, the first part is easy. To determine the maximum number of real zeros that the polynomial function can have, the theorem is number of real zeros theorem on page 241 says a polynomial function cannot have any more real zeros than its degree. So, for example, number 11, the polynomial function is this, and it has a degree of 7, which is the largest exponent. And since the polynomial has a degree of 7, it can have at most 7 real zeros. Okay, for the next part, you have to use Descartes' rule of signs, and that appears on page 241. To do that, you account the variations in sign of the non-zero coefficients of the polynomial. So, for example, the first variation in sign, it goes from negative to positive here, so that's one variation in sign. It goes from positive to negative here, so that's another variation in sign. And finally, it goes from negative to positive here, so that's 3 variations in sign total of f of x. So the function f of x has 3 variations in sign of non-zero coefficients. Therefore, there are either 3 or 1 positive real zeros. The reason they tell you 3 or 1 is because according to Descartes' rule of signs, the number of positive real zeros is either going to be the number of variations in sign, which we counted to be 3, or it's going to be that minus an even integer. So an even integer in this case would be 2. So it's either going to be 3 or 3 minus 2. So the possibilities for positive zeros are going to be either 3 or 1. Okay, now to determine the negative zeros that the function can have, we have to consider f of negative x. So basically we rewrite the function putting negative x in for everything that was x up here. We put in negative x, and that gives us this as the function of f of negative x. Now this has, it goes from positive to negative, so that's one variation in signs. Here it's just negative to negative, so that's not a variation in sign. And finally, it goes from negative to positive, so that is a variation in sign. So altogether, there's 2 variations in sign. The first one is positive to negative, and the second one is negative to positive. So we write it all out that the function f of negative x has 2 variations in sign of non-zero coefficients. Therefore, there are either 2 or 0 negative real zeros. Again, the reason it's 2 or 0 is because the answer is going to be either the number of variations in signs, which we determined to be 2, or it's going to be that number minus an even integer. So 2 minus an even integer 2 is going to be 0. So the answer is they're either going to be 2 or 0 negative real zeros. Okay, the next one is 12. This polynomial here has a degree of 4. So since the polynomial is a degree 4, it can have at most 4 real zeros. If we count the variations in sign of the function f of x, we see that's just positive to positive, so it's not a variation. The first variation occurs here, positive to negative. And then it just stays negative all the way to the end, so there's only 1 variation in sign. So the function f of x has 1 variation in sign of non-zero coefficients. Therefore, there is 1 positive real zero. The reason you don't have 2 possibilities here is because if you take 1 and you subtract an even integer, you're going to end up with a negative number, and you can't have less than 0 non-zero coefficients. So anyway, there's just going to be 1 positive real zero. Next, we consider the function f of negative x. Again, we put negative x in for all of the x's that are up here, and that converts the function to this. The function f of negative x equals this. So let's go ahead and see the variations in sign here. Here's positive to positive, not a variation in sign. Here's positive to positive, excuse me. Here it's positive to positive, not a variation in sign. There's only one variation in sign, and that's when it goes from positive to negative. So just like f of x, f of negative x only has one variation in sign of non-zero coefficients. Therefore, there is one negative real zero. So this function is going to have one positive real zero and one negative real zero. Okay, moving on to the next one, 17. Here our polynomial is of degree 4. Again, that's the highest exponent in the function. And since the polynomial is of degree 4, it can have at most 4 real zeros. If we count the variations in sign, it goes from negative to positive. That's one variation in sign. And then it goes from positive to negative. That's another variation in sign. So the function f of x has two variations in sign of non-zero coefficients. Therefore, there are either 2 or 0 positive real zeros. Incidentally, I was looking up here. I should have wrote that. Therefore, there is one negative real zero, but I think I left out the there in that sentence. So remember that and put that back in if you need to. But as far as 17 goes, the function f of x has two variations in sign of non-zero coefficients. Therefore, there are either 2 or 0 positive real zeros. And then we consider f of negative x. That turns out to have, goes from negative to positive. That's one variation in sign. Goes from positive to negative. That's another variation in sign. So just like the f of x, f of negative x also has two variations in sign of non-zero coefficients. Therefore, there are either 2 or 0 negative real zeros. Okay, for 22, the function is x to the 6th plus 1. And again, since the function is of degree 6, it can have at most 6 real zeros. This particular function doesn't have any variations in sign. It's positive all the way through. So the function f of 6 has no variations in sign of non-zero coefficients. Therefore, there are 0 positive real zeros, or no positive real zeros. And then we consider f of negative x. Actually, if you replace x with negative x, it's not going to change it at all because x to the 6th and negative x to the 6th are the same thing. So x to the 6th plus 1, or f of negative x, also has no variations in sign, and therefore there are 0 negative real zeros. So this particular function isn't going to have any zeros whatsoever. And actually, if you think about it, that makes sense because this function is x to the 6th, shifted up the y-axis by 1, so it's going to, sort of look like, not quite like x squared. It's going to have a flatter bottom to it, and the sides are going to go up more vertically, but it's basically going to look like sort of like a parabolic function, but instead of being at the origin, it's all shifted up the y-axis by this 1 because this plus 1 makes it a vertical shift, and therefore it's never going to cross the x-axis, and therefore it's not going to have any zeros. So the answer worked out to be correct. Okay, well, we're done with that section.